Welcome back to our last section in probability distributions and expected value. Today, we're going to learn how we can use probability to make decisions and predict outcomes over time. One of the main ideas we'll focus on is called expected value. An expected value tells us the average result we would expect if something happened many times. We'll learn how to calculate expected value, we'll interpret what it means, and use it to make decisions in real world situations involving things like games, money, and other probabilities. To start with, we're going to look at the expected value formula, um, which is, again, the long-term average result of something happening. So we write expected value EX. The mean of X is mu X. That's what that letter U is. It's mu. Mu is how we spell it. Um, is mu, and that's the average or the mean of X. And so the expected value, I wrote two different ways to find expected value. I like this first way because I think that it shows us what's being multiplied and added together. So if we have multiple values of X, at all with different probabilities, which we saw in the last lesson with table data of probabilities, we can find the expected value of anything if we're given the probability of each variable. So we multiply the probability of when X is, let's say X is 1 times the probability when X is 1 plus when X is 2 times the probability when X is 2, all the way through Xn times Pn. So again, X is the possible values of X, and P is the probability of each value. And we can write this in summation notation. I wrote this the second way here. This is just in summation notation. These both mean the same thing. But if you were writing it out as an equation, we're going to use this equation. I think that's going to make a little more sense. That's in the expanded form. So we multiply each X by its probability and then add the results together. Couple other key terms. Expected payoff is the expected value when the outcomes involve money. And a fair decision, that's where each option has an equal chance of being chosen. Okay, so for a decision to be fair, each person should have an equal probability of being chosen. We'll calculate the probability of each possible result and then compare them. If probabilities are equal, the decision is fair. If the probabilities are not equal, then we say the decision favors one person over the other. Okay. So for example one, we're going to check to see if this is a fair decision or not. A standard deck of cards has 52 cards in it. And this is something we're going to see quite often with probability. There's 4 suits, 13 clubs, 13 diamonds, 13 hearts, and 13 spades. Clubs and spades, those are the black cards. Diamonds and hearts are the red cards. Two people, Kenny and Asia, are playing a game that involves drawing 2 cards from a deck of cards to start the game. They draw these cards with replacement. So when they take a card out, they see what the card is, they put it back in the deck. So with replacement means that our denominator for our probability is going to stay the same because they're putting it back before they do another trial. So our denominator, if we're talking about all the cards total, is 52. And it's always going to be 52 with replacement. Okay, so they replace the first card and shuffle before drawing the second card. If both cards are the same color, both red or both black, then Kenny goes first. Otherwise, Asia goes first. And it says, is this a fair way to decide who goes first? Why or why not? And it says, no, there's a higher probability that Kenny will go first. So no, it's not fair. Or no, it's not fair and Asia might go first. Or yes, it's fair and they have the same probability of going first. So there's 2 ways that Kenny can go first. So for Kenny, the ways that he gets to go first, he wants to go first, we can say this is a positive outcome for him. So there is way number one for him to get a positive outcome is that he gets two cards of the same color. So the probability that he gets a black card, puts it back, and probability that he gets a black card again. The second way for Kenny to go first is the probability that he gets a black card, or excuse me, a red card, and the probability that he gets a red card. So it says they have to both be the same color. So that's for if Kenny uh, is successful. For Asia to be successful, there are two different ways that Asia can get to go first, or that she gets to win in this example. So if she gets to go first, then there will be a black card and a red card. Or the second way that she could be successful is that she gets a red card and then a black card. Okay, so those are the four total ways that these people can succeed or not. So for Kenny, the probability of getting a black card is 26 out of 52. There's 26 black cards and there's 26 red cards. Then he puts it back, denominator stays the same. There's also a 26 out of 52 chance. Same thing for the red cards. There's a 26 out of 52 chance to draw a red card. And to draw a red card again, the probability is 26 out of 52. He puts the card back, so there's still 52 cards in the deck. If we simplify this, this is 1/2 times 1/2, which is 1/4. So he has a 1/4 chance of getting a black and a black card. And that's also 1/2 times 1/2, which is 1/4. So he has a 1/4 chance of getting a red and a red card. So for Kenny to be successful, for him to go first, we would add these probabilities together, which means he has a 1/2 probability or 50% chance of going first. Okay. Now, Asia probably also has a 50% chance because 100% minus 50 is 50%, but let's just do the math on this anyway. So the probability that Asia gets a black card is 26 out of 52. Puts the card back, still is 52 cards. She's getting a black card and a red card, so we're multiplying probabilities. There's 26 red cards also. That's also 1/2 times 1/2, which is 1/4. And same thing here for red and black cards. For a red card, there's a 26 out of 52 chance that she gets a red card on that first draw. And there is also a 26 out of 52 chance that there's a black card on the second draw because it's with replacement. Our denominator stays 52. So this is 1/2 times 1/2, which is equal to 1/4. So yeah, we're going to add those together, and Asia also gets a 1/2 or 50% chance of going first. So this is a fair way to decide who goes first. They have an equal probability of figuring out who goes first. Okay. So I think it's always good to look at probability problems with cards because just knowing some of the basics about a deck of cards is important. And then also recognizing that with replacement keeps the denominator the same. Without replacement means that our denominator would decrease as we keep taking cards out of the deck. Okay. This next example is with dice. And I've found a couple of diagrams here for us to see this problem a little bit more clearly. So what these two diagrams are showing is rolling two dice. So we're rolling two dice and then finding the sum of those dice. So if somebody rolls a 3 and a 4, the sum is 7. Somebody rolls a 4 and a 3, the sum is also 7. So this is a sum of two dice table, if you want to look those up yourself, or you can take a screenshot of the sum of the dice table. I think these are just kind of handy to have for probability problems in general. So Miguel and Jordan, they're rolling a pair of dice, six sides on each of the dice, and they want to decide who has to vacuum the apartment. If the sum is seven, Miguel will vacuum. If the sum is three or four, then Jordan has to vacuum. If it's anything else, they'll roll again. So they're only concerned with when they add the dice that if it equals seven, Miguel has to vacuum. If it equals three or four, Jordan has to vacuum. We want to know, is this a fair way to decide who has to vacuum, why or why not? So Miguel, I wrote Miguel's here. We'll start with him. The sum of the dice is seven. So he could get a six and a one, that makes seven. He can get a five and a two, that makes seven. Four and three makes seven. Three and four makes seven. Two and five makes seven. And he could roll a one and a six to make seven. Now there's 36 possible outcomes here. And it looks like we have one, two, three, four, five, six ways to get a seven out of 36, which is 1/6 of a probability if we wanted to reduce that. For Jordan, he wants to get a sum of a three or a four. To get a three, he could get a two and a one and a two. And I think that's it for threes. To get a four, he could roll a three and a one, a two and a two, and a one and a three. And that's all of our threes and fours for Jordan. So there's one, two, three, four, five out of 36 ways for Jordan to get those numbers. So it says, is this a fair way to decide who vacuums or not? This is not fair. There's a different probability. Miguel has a higher probability that he has to vacuum the apartment. Not by very much, but still, it's not exactly a fair way to determine who has to vacuum the apartment. Okay, the next part is on expected value. And this sometimes is described as the mean of a discrete random variable. It's the expected value. So um, the expected value tells us the average result we would expect over many trials. And to find it, we multiply each possible value by the probability and then add the results together. And that was that first equation that we saw in the beginning of this lesson, where our expected value, they're using h here. I'm just going to write it as ex just to keep things simple and to make sure that if you wrote down the notes from earlier, that it matches your notes. So this is the first value of x times the probability when x is the first value of x, plus the second value of x times the probability of the second value of x. And we continue that pattern like that. Let's look at this actual problem here, though. It says um, Cora is flipping three coins at once. Here's the probability distribution for the probability of her getting zero heads, one head, two head, or all three of the coins landing on heads. And she has the table of the probability distribution. We want to know the expected value of the number of coins that will land showing heads, which means on average, how many of these coins, if she flips three coins at a time, are going to show heads as the coin flip. So this is going to be, we're going to write this as the expected value of h is equal to our first data point, x1, is actually when heads is zero. So that's zero times, and then that probability of h equals zero is 0.125. Okay, and the second one is when she gets one head times that probability is 0.375 plus when she gets 2 heads, that probability is 0.375, plus when she gets 3 heads, that probability is 0.125. Now, the expected value of the number of heads when she flips all 3 coins, this 0 times 0.125 is just 0, plus, looks like we get 0.375, and 0.375 times 2, 2 times 0.375 gives us 0.75, plus 3 times 0.125 is 0.375. Now we're going to add these together. 0.75 plus 0.375. And we get an expected value of the number of heads is 1.5 heads. Okay, so we can't really get 1.5 heads. It's sort of like when we talk about average amount of children per household. And sometimes you'll hear there's 1.8 children per household or something like that. You can't have 0.8 of a person. You also can't have 0.5 of a head on a coin flip. It's either heads or tails. But this just means after doing this one time. So she flips the coins, all 3 coins one time. This is the expected value, 1.5 heads. And that's our answer for this. But to put some more meaning behind what this answer is, if she did the trial, let's say 10 times, then we could say that 10 flips of these 3 coins, that would equal 10 times our expected value of 1 flip, which is 1.5. We would expect there to be 15 heads. And so we can multiply this number out to get a whole number where it would actually make sense. So I just wanted you to take note of that. So this is the expected value of one trial. In this case, one trial is she's flipping all 3 coins at the same time. So she's taking 3 coins, throwing them in the air, and seeing what they land as. Okay, next one is about somebody in a bicycle shop working as a salesperson. Kelsey records the number of bicycles she sells on a daily basis. It says here's the probability distribution of B, the number of bicycles Kelsey sells on a randomly selected day, and T, the time she spends filling out daily sales reports. Find the expected value of the amount of time Kelsey spends filling out daily sales reports. So we want to find the expected value of time. We have bicycles and time. We don't need to know how many bicycles she sold. We just want to know the expected value in terms of time, and we have the probability here. So B is irrelevant. Just going to cross that out. So we want to find the expected value of how much time that it takes her. So when T is equal to 0, that probability is 30%. When T is equal to 10, that probability is 50%. When T is equal to 20, that probability is 15%. And when T is equal to 30 minutes, T is equal to 30 minutes, then there's a 5% probability. Okay, so now we're going to find the expected value in terms of time. I'm just going to multiply these out. So we get 0 plus 5.0 plus 3.0 plus 1.5. And the expected value of time is equal to 9.5 minutes. And this actually, I think this answer makes a little more sense because 9.5 minutes is attainable. We don't have to find a whole number for it to make sense. So that's the expected value of the amount of time that she's going to spend filling out sales reports. Okay, now we're going to interpret expected value. So we just went over how to calculate it, but we're going to focus on what this value actually means. So remember, the expected value represents an average over many trials. It doesn't necessarily tell us what will happen in one individual trial. So we'll use the idea of expected value to decide whether different statements about an expected value are reasonable or not. So here we have two people, and they're making some statements based on um, probability or expected value. So it says Lisa and Carlos own a hardware store. They sell a certain type of light bulb in packages that each contain 24 light bulbs. The back of each package says the expected number of broken or defective bulbs per package is 0.25, or 1/4, if we want to write it as a fraction. Okay. Lisa says if we look at 100 packages, we expect to see a total of about 250 broken defective bulbs. Carlos says any given package most likely contains 0.25 broken or defective bulbs. Let's look at these statements separately here. Lisa, we know that the expected value is 0.25 bulbs per package. So if we find the expected value for 100 packages, we would say that that's 100 times 0.25. That gives us an expected value of 25. And it looks like Lisa's saying we would expect to see a total of 250 broken bulbs. I don't think that's right. So our expected value is going to be 25. So Lisa is incorrect with her statement. Let's look at what Carlos said. Carlos said any given package most likely contains 0.25 broken or defective bulbs. So what Carlos is saying, he's saying that every package would have 1/4 of a broken bulb. And that really doesn't make any sense. He's saying that every package, that's the same thing as any given package. So he's saying every single package has 1/4 of a broken light bulb in it. And that doesn't make sense. We can't have 1/4 of a broken light bulb. And also, we cannot say that every single package is is whatever that number is, because the expected value just says that we would expect that for every package. There's 1/4 of a bulb, but that does not necessarily mean every single one has 1/4 of a bulb that's broken. So neither person is correct here. Let's look at one more of these with making statements based on probability or expected value. Richard and Cameron buy a carton containing 6 eggs. The back of the carton says the expected number of broken eggs per package is 0.12. Richard says the probability that one of these cartons contains a broken egg is 0.12 on average. Cameron says for every 100 packages like this, we'd predict about 12 broken eggs in total. Whose statement is correct based on the expected value? Richard, Cameron, both of them, or neither of them? So if we look at what Richard says, he says the probability that one of these cartons contains a broken egg is 0.12 on average. Well, the probability is not expected value. I'm going to write Px is not equal to Ex. Those are two different things. So Richard is not correct. The probability is not 0.12. That's the expected value. Cameron says For every 100 packages, we would predict about 12 broken eggs in total. Well, let's see here. If we use the expected value, we have 100 packages of eggs, and the expected value is 0.12. When we multiply that out, we would get 12. So yeah, we would expect 12 eggs to be broken in total if we took 100 packages, like of those packages there. So yeah, only Cameron's statement is correct. Okay, next we're going to look at expected payoffs. And this is our last section on this lesson. We're going to apply expected value to situations that involve money. And this is called expected payoff. So we'll look at the possible gains or losses, multiply those values by the probability, and then add them together to find the average amount we would expect to gain or lose over time. Essentially, we're calculating the expected value of two or more scenarios happening, and then we add the results together. Just an important note is that a net gain can actually be a negative value, which is technically a loss, but we call it net gain. All right. So this first one says a mobile phone company gives customers an option of purchasing a screen protection plan. This is an insurance plan where the customer pays $60 for the plan, and then if their screen gets damaged, the company will replace the screen for no additional charge. So they pay $60 up front for the insurance, and then if it breaks, they don't have to pay any more money. The company knows that only 8% of customers who buy this plan end up actually needing their screen replaced. And they also know that replacing the screen costs the company $250. And it says, here's a table that summarizes the outcomes for the company's perspective. So we have the cost and the net gain. We're mostly concerned with our net gain for this problem because it says calculate the expected net gain or the expected value of the net gain. So let's first think about where they're getting these numbers from, because sometimes we don't have these tables. So the first situation is, the first situation is the customer pays $60 and never needs their screen replaced. That means the company gains $60, didn't have to pay anything out, and everything worked well for the company. The second situation is the customer pays $60, their screen breaks, they bring it into the store, and then the company has to fix the screen, which costs the company $250. Well, the company got $60 already from the customer, so they didn't lose $250 by having to pay for the customer's screen. They lost $190. So loss of $250 plus the $60 that they got from the customer means that the company only lost $190, or they had a net gain of negative $190. So that's how we're getting those numbers there. Okay, we don't have the probabilities listed in our table though, and I'd like to write them in our table. So the probability, I'm just going to write PX, probability of X occurring. So the probability that somebody needs their screen replaced, there's an 8% chance, or 0.08 for our probability. Then there's a 0.92 or 92% chance of the screen never breaking. So an 8% chance the company loses $190, 92% chance the company gains $60. So now we can calculate our expected value for this. And this is the expected value for the company, not the customer. So we're going to write our first X value of negative $190 times the probability, which is an 8% probability, plus $60 times a 92% probability that they just make the $60. Okay, now this is, when we multiply this out, we get negative 15.2 plus positive 55.2. And we're going to add these together. And we get exactly 40. And that's a positive value. So that means that the expected value for each plan, screen protection plan that's sold for $60, the company's net gain is $40. That's how much that they would expect to gain from every customer who buys a screen replacement plan. Okay, we're going to look at two more of these. This next one is very similar to the first one. Here we have an insurance company that's offering renter's insurance. The renter's insurance is $40. They have some probabilities based on some historical data that they've collected in the past, and that there's a 1 in 500 probability that a customer with this plan makes a claim. And it says, and in those cases, the average payout from the insurance company to the customer was $5,000. Okay, here's the table that summarizes those outcomes. So here it says, if the customer made an insurance claim, the company has to pay out $5,000. The company doesn't lose $5,000 though, because they charge the customer $40 in the beginning. They would lose $4,960. So not quite 5,000, but very close. We do have to include the $40 that was initially given to the company though. So that's their net gain. If nobody makes a claim and if no one makes an insurance claim, the company gets $40 and doesn't have to pay anything. So they just get the $40. But now we're going to look at our probabilities. So, right, probability of X occurring. So the probability that someone makes a claim is 1 in 500. It's kind of strange to see as a fraction. So let's figure out what that is as a decimal. That's 0.002 or 0.2%. There's a 0.2% chance that the company's got to pay $4,960 for an insurance claim. If no one makes a claim, that's 499 out of 500 probability that no one makes a claim, or 0.998 is our probability, which is a 99.8% chance that the company makes $40. Okay, now we're going to find our expected value for this. So the expected value is our first amount is the net gain of negative 4,960 times our first amount's probability, which is 0.2%. That's 0.002 plus our second value is positive $40, and there is a 99.8% chance that they make $40. That's 0.998. Okay, now we're going to multiply these. Negative 4,960 times 0.002 gives us negative 9.92. And 40 times 0.998 is 39.92. We're going to add those together, and we get an expected value of exactly $30. Okay, so even though this insurance company has to pay almost $5,000 for an insurance claim, their expected value of selling a $40 renter's insurance plan, they're still expecting to gain $30 on this insurance plan for every insurance plan sold. Okay, so far we've had two positive values of expected value. Let's look at our last example. This one is about a lottery question. And this next problem does not give us a table, so it's a little bit tougher because we don't have a table to look at, but we can figure this out with determining the values of the net gain and the probabilities, making just our own table, so to speak. So it says a pick two lottery game involves drawing two numbered balls from separate bins, each containing balls labeled from 0 to 9. There are 100 possible selections in total. So the lottery ball could say 00, 01, 02, all the way to 99. Players can choose to play a straight bet where the player wins if they choose both of the digits in the correct order. So 9-8 is obviously different than 8-9. There's 100 possible selections. The probability that a player wins a straight bet is just 1 out of 100. The lottery will pay you 50 cents on every $1 bet. So the player's net gain if they win is positive $49. And it says, let X represent a player's net gain on a $1 straight bet. Calculate the expected net gain, EX. And it says the net gain can be negative. Okay. So let's start thinking about what happens when we win or when we lose at this game. So the probability that we win, we have a 1 out of 100 chance to win is what it said. Or I'll just leave it as a fraction this time just to kind of switch things up a little. So 1 out of 100. And our net gain for this is positive $49. The probability that we lose at this game is 99 out of 100. But if we lose at this game, we only lose $1. Still, there's a 99% chance that we'll lose at this particular game. So to calculate the expected value is 1 out of 100. That's our probability. Actually, let's start with we'll do the same order as we did before. I was just switching the order. Let's start with our net gain, our X value of 49, and multiply that by our probability, 1 out of 100. Now we're going to add our next X value of our net gain times our probability of that X value. And this is going to be negative $1 times 99 out of 100. And I'm going to leave this as a fraction. You can actually solve this without a calculator if we leave it as a fraction, because that's just 49 over 1. 49 times 1 is 49. 1 times 100 is 100. So we have 49 over 100 plus, and this is negative 1 times 99 is negative 99 over, and this is negative 1 over 1. 1 times 100 is 100. Just some quick fraction review. The expected value now is 49 plus negative 99. That's 49 minus 99, which is negative 50 over 100, which is negative 0.5 or 50 cents. So we'd expect to lose 50 cents or $0.5 for every time we play this game. So this game only costs $1. You could win 50. But if we were to play this game over and over and over again, many, many times in a row, our overall expected value per game would be we would lose 50 cents. And so you could calculate this into if you tried this 100 times, if you tried this 1,000 times, overall, you would end up losing money with this game. Okay, so for every time we bet $1, we would lose 50 cents playing this game. All right. So I wrote just a quick summary here. And to summarize this lesson, we looked at how probability can help us make fair decisions and predict what we might expect to happen over time. Uh, First, we looked at fair decisions. If people are using a random process to make a decision, we can calculate each person's probability. And then if they have an equal chance, the decision is fair. If one person has a greater chance, then the process favors another person and it's not fair. And then we learned about expected value, which is the average result we would expect over many trials. And to calculate that, we would multiply each possible value by its probability and then add all of those results together. Remember that expected value doesn't necessarily tell us what will happen on one individual trial. So for example, an expected value of 1.5 heads doesn't mean we actually flip 1.5 heads. It just means that over many rounds, the results would average out to about 1.5 heads per round. And then we could take that number and multiply it by the number of rounds to get a whole number if we needed to. And then finally, we looked at the expected payoffs, which is really just expected value applied to money. Some outcomes may represent money gained, while others represent money lost, which is why a net gain can sometimes be negative. So overall, expected value uses probability to tell us what we should expect on average over the long run. Okay. All right. So that is everything on decisions with probability and expected value.